Hello, dear students. Welcome to the channel and very welcome to this playlist in which we are discussing about 8085 microprocessor. Up until now, we have seen pin diagram, architectural block diagram. We have seen uh, different registers, how we can save our program in memory, how do we classify the memory. We have seen the basics of programming in 8085. We have seen the machine cycles, and in continuation to previous class, today we are going to discuss about the timing diagram in 8085. Now, it is important to understand the difference between the machine cycle and the timing diagram. Machine cycle exists for one particular instruction, or one particular thing that you want to execute, right? Like you can say for fetching the opcode, or copying content from register to memory, or memory to register, or input device to memory, right? But the timing diagram is used for specific purpose, from moving my content from register R2 to register, sorry, from register RC to register RB, right? So specific register targeted somewhere. Machine cycle is generalized, timing diagram is not generalized, right? It is specific. And the first timing diagram that we are going to see today will be the instruction, as you can see here, move R1 comma R2. Or you can also, if because I've told you that it is specific, let's say RB comma RA, right? So remember previous class, what did we learn in the previous class? That the the register on the right hand side, or address on the right hand side, or whatever it is on the right hand side, is the register that holds the value, right? The one which will transfer the content to the register in the left hand side. That means RB comma RA, that means RA is holding the value and it is about to transfer that value in the RB, right? R2 comma R1, that means R2 is holding value and it is about to transfer that value in R1. So that is what going to happen here. By the way, if you want to learn about it in very detail, you can check out the previous class video. The link will be flashing on the top right hand side corner of your screen in the I button, so you can click on it and you can check out that video. And if you have already seen it, let's move forward with today's class. So now that out of the way, then timing diagram is sometimes set of multiple machine cycles, right? So it can be possible that if I'm going to execute some timing diagram, then I will have to use multiple machine cycles. I have to use opcode fetch, I have to use memory read, dependent based on whatever requirement that my timing diagram, my instruction requires, right? So let's first see this one instruction, move R1 comma R2, which says the content of R2 is going to be moved in R1 register. And remember, whenever we had transfer, register to register transfer, that instruction always holds only 1 byte, right? That means that is only a 1 byte instruction. So this instruction doesn't require data from memory, and no and it doesn't store any data to memory as well, right? So there is no exchange of content with memory here. It's exchange of content between two registers. Simple enough. So only opcode fetch machine cycle is required to fetch and execute this instruction, right? And simple, when you have 1 byte instruction, you will generally will be required only one cycle. Now remember, opcode fetch used to have around 4 to 6 t states based on whatever requirement is. Here the requirement is of 4 state, because initially, remember, we always draw 4 state, and if it is required further, then only we draw the state number t state, t5 and t6. So first we will have the clock signal, as we saw in previous class. Then in opcode fetch, what happens, the content of a to a15, it will be stored in the program counter, which will be pointing towards the register h. The higher order address will be stored in a to a15, which will be pointed to register h by program counter, and it will go till three stages, three t states, right? And what about the lower order address? It will be pointed by the register L in the program counter, and it will be stored during the stored in the AD0 to AD7, and it will take place only during the T1 state. Again, same ALE will be activated during the first T state only, as we have seen in opcode fetch cycle previously. Same thing will happen with IO machine. It will go from 1 to 0. Now during the second state and the third state, the opcode fetching takes place, and here always remember what we are doing. We are reading and pasting. We are doing what all we are doing is reading. So here the read will be activated, right? During opcode fetch, the read command will be activated and opcode will be fetched. Write will stay high all the time, and always remember what is the status of opcode fetch cycle. It is always s0 equals to 1, s1 equals to 1, right? So again, I'm repeating one more time. For this cycle, the address is given by program counter, and program counter is incremented by 1 to the point to whatever next instruction. Now this instruction, can anyone tell me, does this instruction requires T5 and T6 stages? Will there be any changes if we draw the T5 and T6 states? Right, there will be no changes at all. So we don't need T5 and T6 stages. So timing diagram will be limited to this only, just one, opcode fetch. But now what if I have to execute this instruction? This time I'm moving the content from data to my accumulator or register A. So in this case, how many machine cycles do we need? We will need opcode fetch for fetching the opcode, plus the operand fetch. Opcode fetch and operand fetch. We will be needing, will be requiring 2 machine cycles. And how are we going to execute it? So first we will be drawing the opcode fetch as it is, and we all pretty much know how does opcode fetch as a machine cycle takes place. How do we draw it? So you simply have to draw it, and after that just draw the operand fetch. First, what you can do, you can draw the 4 states of opcode fetch. Then again, clock signal A to A15 will perform the same task. AD0 to AD7 will perform the same task it was performing earlier. Same thing will happen for ALE, IO read, read, write, and status signals. And the opcode fetch machine cycle will remain same as what we saw in previous case, but the next cycle from the fifth t state, if we can count in continuation, then it would be fifth t state. If we end four t states of opcode fetch and then start the operand fetch, then it would be t1 state. So I'm counting in continuation even though they have written t1 here. So the t5 state, the operand fetch cycle will be executed. Still the clock pulse is going the same way as it was going earlier, but this time see, the A8 to A15 is again having PCH, and this time 80 to 87 is again having PCL, right? So still the H and L are pointing the program counter to uh, for higher order address we are having A8 to A15, and for lower order address my L register is pointing the program counter to 80 to 87. And then again the reading is taking place. Let's say I want to print some data 35H, so it will be printed during the T2 and T3 states, and during the same time the read cycle will be activated. Remember the status signal for operand fetch is S0 equals to 0 and S1 equals to 1, so make no mistake, in this case ALE will be activated on the first T state of every machine cycle. So this is the easy way to understand or remember when the ALE will be activated. So ALE will be activated during the first T state of the machine cycle, or the first T and the first T state of the next or upcoming machine cycle. And if I ask you that how many bytes does this instruction MVI A comma data requires, so what would be the answer? So this MVI A comma data will require 2 byte. This is a 2 byte instruction because it is operating with two different cycles, because it is operating with two different cycles, opcode fetch, operand fetch, two different cycles. And cycles, by cycles I mean machine cycles, okay? Don't confuse it with instruction cycle or timing cycle or any other cycle, okay? It means machine cycle. So for example, uh, in order to execute this instruction it doesn't require any data from memory, right? So only two machine cycles are enough. And here one more thing which I would like to point out, that what instruction we are executing exactly, because I told you earlier, when we talk about the timing diagram we go for specific instruction, including if I'm writing data it would not be sufficient, I have to mention what data, right? So let's say 35H, because we have drawn 35H here. So during opcode fetch what will happen, the address is given by program counter, right? For opcode fetch cycle the address is given by program counter and it is incremented by 1, and now it points where the operand is stored, right? So this 3EH is what is it doing? It is pointing where the operand is stored. And what will happen during the operand fetch? So for operand fetch cycle the address is given by the program counter, and the program counter, apologies, and the program counter contents are used to read the operand. So the data is read from the addressed memory location into the specific register, and again program counter will increment it by 1 point, and next instruction after this MVI instruction. And same timing diagram is applicable to the instruction like ACI data, ADI data, ANI data, CPI data, ORI data, SUI data, SBI data, XRI data, MVI. So all these instruction, don't worry about it, we don't have them in syllabus. If you want me to cover them, we can cover that as well. But right now let's move forward to the third cycle of today, or third timing diagram for today. It's MVI M comma data. So first question that I'm going to ask is, see how many machine cycle does it have, and tell me how many bytes will it require. Right, there are 3 machine cycles, so 3 bytes. So in MVIM comma data, the HL register is used. As you can see, we have used HL register, we used HL previously as well, but by default as a memory pointer, which we always do. As you can see in the opcode fetch and operand fetch as well, we are using HL as a memory pointer. But as I've said, this instruction loads 8-bit data specified within the instruction to the memory location, which is pointed by HL register pair. And as we are taking 3 machine cycles, it will be 3 byte instruction, right? Now we have already seen opcode fetch and operand fetch machine cycles, so I'm not going to explain both of them again. You just have to draw opcode fetch and operand fetch the way we always draw. Same way, opcode fetch will have 4 t states, operand fetch will have 3 t states, and based on the next operation you have to decide what will be your next machine cycle, or what will be your next cycle in order to execute your instruction accurately. So, and for that it is important to understand the purpose of each and every machine cycle, right? So because if you wouldn't have understood the machine cycle's purpose correctly, then there would be no point on discussing the timing diagrams, because timing diagrams would be useless without the machine cycles, knowledge of machine cycles properly. So first will be opcode fetch. We already know what will happen in opcode fetch. Second one is operand fetch. We also know what will happen in operand fetch. One thing, interesting thing which I want to point out, that the opcode fetch is using program counter to fetch the opcode program memory, right? Let's say what data is it holding. Let's say it is holding 36H. In the operand fetch is very much similar to memory read. Also, you can also call it memory read cycle as well, right? So in operand fetch or memory read, it will also again use the program counter to fetch the data from the program memory, right? Like the data given within the instruction is read, so program counter is will be incremented then by 1 point, and it will move to the next instruction, right? So that is what operand fetch is going to do, right? So every single time you have to read, you have to write something. So in order to write something, first you have to read it, and that's why we are using this operand fetch here. Then we have the memory write. So HL content will appear on the address bus, and write signal will be generated to perform the write operation in the data memory. So the data is written at the address specified by whatever HL register is, right? So here what is happening, I'm repeating one more time. So whatever content HL register hold will be shown in the address bus. So this write signal will be generated to perform the write operation in the data memory. As you can see, this during the T, which state would it be, 4, 5, 6, 7, 8, 9, T9 and T10 state, this write signal will be activated, and you will write your data in the memory, right? Whatever the address specified by HL register pair. Then we have next instruction, move m comma r. So here what we are going to do, we are going to move something that exists in the register to some memory address, some pointed memory address, right? So the content of specified register will be written into the memory location specified by HL pointer, right? Whenever we execute this instruction. So again we are using two different machine cycles, opcode fetch and memory write. Always remember, whenever we are going from register to memory, you don't have to use the memory read, but whenever you are uh, going from memory to somewhere, you have to mention, you have to read it first. We are going from register to memory, so if it exists in the register, that means it has already been read, so you don't have to execute the memory read one more time. See, here on the right hand side we had data, so we had to use the operand fetch or memory read. Here also on the right hand side we had data, so we have to use the operand fetch. But here we were moving from register to register, so we didn't use operand fetch or memory read. And again one more time, see, here we are again moving from register to memory, so we are not using operand fetch or memory read cycle. So that's the main motto. Then again opcode fetch will be executed. I'm not explaining everything one more time for opcode fetch, and after opcode fetch memory write will be executed. Same thing will happen whatever happens in memory write, so I'm not explaining everything again, but simple, the clock signal will be there, 4 states of opcode fetch plus 3 states of memory write, which means there will be total 4 plus 3, 7 states. As we are having opcode fetch and memory write, two instructions, that means it will require 2 bytes, instruction will require 2 bytes. And again HL register pair are pointing the memory location. Higher order address will be stored in the H register, lower order address will be in the L register, and the data will be written during instruction during the T states 6 and 7. There are total 7 states, so in final 2 states the data will be written, right? And that's what the whole purpose of the memory write cycle. We write data. Now tell me, we are going what are we going to do? We are doing move r comma m, right? R comma m. So we are moving the data from memory to register. What will we do now? What will be the correct two machine cycles? Opcode fetch will be there. It is pretty much simple. Opcode fetch will come into the action for sure. But what will be the next machine cycle we will be using this time? See, we only have to paste the memory in register only. So whenever we go for register, always remember, if you are going from register to memory, if you are going from register to memory, then you don't have to include the memory read cycle. So whenever r is in the left hand, whenever r is on the right hand side of your instruction, you are not going to include the memory read cycle. If r is on the left hand side of instruction, that means memory read is required. See, here r we are having on the left hand side, which means register is on the receiving end, and whenever register is on the receiving end, we always include memory read cycle. So again, first cycle will be opcode fetch, second will be memory read. The instructions will be same, there will be no change in the signals as well. Total number of t states will be 4 plus 3, so total 7 t states, again same as the previous instruction, but only change this time we have here is, instead of memory write, we are having memory read here, because we are moving the content of some memory location into the register. So that is why we are including the memory read machine cycle. Other things will remain as it is, so we are not going into the details. One more thing, this instruction uh, contains two different memory cycles or machine cycles, and because of that this instruction is 2 byte instruction. Simple. And again, as earlier as well, the instruction is transferring the content of memory location pointed by HL register pair to the register pair specified to the instruction. That means the address of the memory will be given by HL register pair only. And to take the data from the memory, it requires the memory read operation, right? And that is why we are using memory read to take the data from the memory. First, opcode fetch. What will happen during that opcode fetch cycle? The program counter places the address on the higher order add and the lower order bus. So the H register places the address on higher order bus, and L register will place the address on the lower order bus. And this opcode fetch cycle will fetch the opcode from program memory using program counter, and then program counter will be incremented by 1, and then it will move to the next instruction. During memory read, the address will be specified by HL register as its memory related operations. The data present at the memory location pointed by HL register pair is read into the specific registers. So the PC is then incremented by 1, and the point is and it will be pointed to next instruction. PC means the program counter, by the way. So that was the move R2M. The next and the final instruction which I want to discuss would be STA address. And as you can see, it is having total 4 different machine cycles, and we are going to discuss that as well, right? Why we are having 4 machine cycles. So firstly, what does this STA address stands for? That you need to understand, or you need to grasp or tell me. So the STA loads the content of a register to the memory location whose address is specified in the instruction. Okay, and as you can see, we require 4 machine cycles to perform this operation, and because we need 4 machine cycles, it would be 4 byte, of course. First machine cycle, as you can see, will be opcode fetch, and I'm not explaining the whole cycle one more time because we have done it around 7 to 8 times now. So in simple language, the program counter will place the address on the higher order address using H register, and on the lower order address using L register. Cycle will fetch opcode from program memory using program counter during the T2 and T3 states, and then program counter will be incremented by 1, and will move to the next instruction. Now the opcode for this instruction will be 3AH. Then it will go to operand fetch or memory read. Now there is one instruction there is one interesting thing about STA address, that we are using total 2 memory read. Opcode fetch and memory read are equal or same, so I'm calling opcode fetch operand fetch and memory read are equal, so I'm calling operand fetch as memory read. So we are using 2 memory read cycles. And why are we using it? So let's understand it. First, let's understand the first memory read cycle. Now the program counter will place the address on the lower order address bus in the memory read again, and lower order address, it will be using L register, higher order address H register. Then lower order byte of address will be specified. Byte of address specified is read using program counter, and the program counter is then incremented by 1. Okay, but the interesting thing is the addresses will have total how many digits? 4 digits. How many digits p and sorry l and h can point out? Only 2. So my address consists of total 4 numbers. H and L can only point out towards 2. So what about the remaining 2 numbers? So for that we are using this memory read cycle one more time, right? Because the address will not be simply STA22 or STA07 or STA32. No, it will go STA 321H, sorry, 321A, STA 0032, STA 1234, something like that, right? So it would be 4 digit, and because of that we need two different memory read cycles. Now in the third memory read cycle, again program counter retains the address on the lower order address for L register, for higher order address for H register. Now higher order byte of the address is read using program counter. So during the first operand fetch, we will be reading what instruction? We will be reading only lower order address. So if my address is 1234, so 34 is only read during the 34 is only read during this M2 machine cycle, and 12 will be read during the M3 machine cycle, right? And then we will be using memory write for writing the data from accumulator to address memory location. And address for this is given by using about two memory read cycles that we have taken for higher order and lower order addresses. And then we were during let's see how many T4 states does this have. 4 5 6 7 8 9 10 11 12 13 states it has. So the data will be printed on the last two states, which means 12th and 13th state. And other things are same as previous memory cycles. We have already discussed all of these memory cycles in detail earlier, so I'm not going into that detail anymore now. So that would be it for today's class. That would be it for this chapter. Next time when we meet, we will we most probably will be discussing about the microcontroller. So if you have any doubts or any queries, feel free to mention them in the comment section below. If you have any suggestions for the videos or for the channel as well, any suggestions and feedbacks are always welcome. I want you guys to speak either good or bad or anything, but I want you to react on the comments so I can understand that if it is going well or not. So we will keep today's class till here. Thank you very much for listening. Take care of yourselves, and goodbye for now.